Hey, pardon the interruption. There was a little bit of a technical issue going on with my doc cam. It was getting kind of skippy. Hopefully it didn't wreck the last video too much. But we're going to start back our calculation with 2010 Form B's FRQ with question E2. So it says to calculate the molar concentration of each species at equilibrium. Molar concentration, when you're dealing with this, remember, has to be in moles per liter or molarity, not in pressure. My first inclination when I looked at this problem was to do it in pressure, and that was not the right call. So when we look at this, make sure that you do it in moles per liter instead. In this situation, if you have to find the concentration of all species at equilibrium and you don't have either you don't have this massive equilibrium constant, you are going to have to use an ice table to figure out those concentrations. So you need to figure out the setup for your ice table. So it's going to be N-butane going to isobutane. And I'm going to set up my ice table. Get that in there. My concentration was 0.01 moles of my chemical per 1 liter. So my molarity in this case is going to be 0.01 molar. And I don't have any isobutane at the start of my reaction. So you know from most of our ice tables that we have a minus X and a plus X showing up in our ice table. And this would be 0.01 minus X and X. Now this is a situation because the equilibrium constant is not very tiny, you are going to have to not be able to lose this minus X in this situation. So I would say this is one of the few situations where you actually have to do it because the K value is pretty substantial and you're going to have to take that into account. So when I set up my equilibrium expression, which I did on the other table, I'm going to have X over 0.01 minus X, and that is equal to 2.5. All right, so now I have to solve for X, which is kind of a pain, but we're going to do it anyways. We're going to have to distribute the 0.01 and the minus X up into the 2.5 to make sure we get that. So we have X equal to 0.025 minus 2X. We're going to bring the 2.5x, we'll put that in there. Bring the 2.5x to the opposite side. So we have 3.5x equaling 0.025. And then when I solve for x, which I'm kind of cramming in here a little bit, I get an x of 0.0071. Okay, so that is molar. So that's the change that belongs in both of these X values. And again, normally we dump this X when we're talking about KSPs and stuff like that, but that's because the KEQ constant is small. This is a pretty big constant, so we can't make that disappear. So in this case, the 0.071, that is equal to the concentration of my isobutane. But to figure out the concentration of my N-butane, I need to take 0.01 molar, and then I need to subtract from it the X value, 0.0071 molar. And when I do that, I get 0.0029 molar for my concentration for both of those. So 0.0029 and 0.0071 molar. Okay? For part 3, it says if the volume of the system is reduced to half its original volume, what will the new concentration of N-butane after equilibrium, what will be the new concentration of N-butane after equilibrium has been reestablished at 25 degrees Celsius? Justify your answer. If we go back to our original equation here, we have a 1-to-1 mole ratio, which if you think about Le Chatelier's principle, okay, Le Chatelier's principle talks about how your systems react to stress at equilibrium. When we talk about gas systems, if there are more moles of gas on one side than the other, if you take the container and make it smaller, the reaction is going to shift away from those moles of gas. However, in this case, since it is a 1-to-1 mole ratio, you are not going to have a shift in equilibrium to one side more product or more reactant. So I'm just kind of, I guess, talking about that here. So in my answer, I'm going to say after the equilibrium reestablishes, the, let's say, ratio of, little dyslexia there, N-butane to isobutane will remain the same. Because of this, when the volume is cut in half, the concentration of both, think about it, if we have a half a liter container now instead of a full liter, what's it going to do? Concentration, if that is, I'm sorry, when the volume is cut in half, the concentration is doubled. Hopefully that makes sense to you. If you have any questions about that, we can clear it up in the meantime. But hopefully that makes sense to you. All right. Last problem for 2010. So suppose that in another experiment, a 0.01 mole sample of pure isobutane is placed in an evacuated container. So instead of starting off with N-butane, we're starting off with our reactant, we are starting off with all product in this container. And then it says, and it's allowed to come to equilibrium, same temperature. Calculate the molar concentration of the species after equilibrium has been established. I'll talk about it in terms of a conceptual idea, and then I'll show you the math to prove it. I think that talking about this as a conceptual idea would be fine, but I'll show you the math, whichever way is your preferred method to explain it. So in this situation, since you have something that's going to be reestablishing an equilibrium either way, and you start off with the same concentration as you did of the other reactant, you are going to establish your equilibrium back in that same position. So if I have the same amount of total chemical moving reactant to product this time instead of, or I'm sorry, product to reactant instead of reactant to product, you are going to end up with the things in the same concentration. I think in my mind, though, it's like, I don't know if I believe that. So I'm going to actually show you the math for that, and I will prove it to you. Okay. On the previous ice table, my 0.01 moles went in for the N-butane. Now they are going in for the isobutane. All right, and I don't have any of the N-butane left. So normally we have a minus X for our reactant. We can't do that this time. Our reaction has to head towards the reactant side to kind of get back to equilibrium. So I'm going to see my minus X showing up on the isobutane side and a plus X over here, which is a little bit different, and that's kind of why I think this is a good problem. 0.01 minus X for my isobutane's equilibrium value, and then X is the equilibrium value for my N-butane, so we should be good to go there. And what we're going to do now is we're going to do the same thing we did before. We're going to put that into our equilibrium expression. 2.5 is equal to 0.01 minus X over X. All right, so it's the same setup, products over reactants, but we have different stuff in here. And you say to yourself, how is this possible that this is going to work out the same? This is where equilibrium is magical. I'm going to carry my X up to the top. So I'm going to have 2.5X equals 0.01 minus X. I want to collect all of my X's. So I'm going to add an X to both sides. And that leaves me with 3.5X equaling 0.01. Okay? Getting X alone, my X equals 0.0029. Uh-oh. So if I divide both sides by 3.5, oh, that number should look kind of familiar to you, and it is. So the molarity for X is going to be the same for the concentration of the N-butane. And now if I want to find my concentration of my isobutane, what I'm going to do is I'm going to take the 0.01 minus 0.0029, and then I end up with 0.0071 molar. And holy moly, it is exactly the same. Again, the reason this works is because I'm starting off with the same concentration on my reactant side and my product side as I did in the previous one. I kind of said that stupidly. So the isobutane's concentration here is the same as the N-butane's concentration was in the first one. So I still have basically the same number of moles of stuff moving back and forth, and because of that, I'm going to end up with my equilibrium position landing in the same spot, if that makes sense. And again, if I make my container bigger or smaller, I may adjust the concentrations, but the math on this is going to stay the same. Okay? Hopefully that makes sense to you. If you have any questions, make sure that you pop into me or shoot me an email, and hopefully then we can clear things up, okay? Good luck!